Okay, aerospace science class, hopefully you have recovered from our field trip. I think that went pretty well. It's a long time traveling to get to a location. We only were on location a little over an hour. But boy, it's really worth it. I just really think that I just want to really encourage you that if you can, bring students out in the field. I know it's a hassle, but it really is worthwhile. I just want to encourage you to do that. You've got my mug down the lower right-hand corner today because I want to show you a few items. My intention is to do a short video on metamorphic rocks. I'll be reaching to my side to grab some samples to show you, to hold up to the camera here periodically, and hopefully make some points. And then there will be followed up by an even shorter video on the lab activity that I want you to do. On Tuesday, so there will not be class on Thursday, so on Tuesday, we will be having, we're about a day behind because of the wedding and such. I intend to go through sedimentary and metamorphic rock identification. We're going to do that a little bit differently. I'm going to have samples out for each group. We're going to go through them one at a time in a very directed manner. It will shorten things up, and then we will move on to astronomy in the second portion of the class. So that's the way class will work a week from Tuesday, so next Tuesday. Anyway, so metamorphic rocks, that's what we're talking about today. We've already had some fun with rock names like granite. Never take it for granted. Well, we're going to expand your rock pun repertoire today because we're going to have some other rocks like this is a metamorphic rock we're going to have today. This is called gneiss. So yeah, so that's a nice rock. Yes, thank you. Yes, I agree. It is a very nice rock. Or this one, you got to do a two-shoulder thing, you know. Kind of see who's looking. This rock is a sample of schist. You must enunciate that. It's not schist, or that's the German word you're trying not to say. Schist. This is a kind of schist. Okay? And we'll learn how to identify those next Tuesday. I had a student come up to me one day and he grabs a pile out of the bin of schists, one of the bins, and he puts it on the table and he says, "So is that a pile of schist?" I said, yeah, I believe it is. And we all got a big chuckle. Anyway, metamorphic rocks. Rocks that have been changed by heat, pressure, or chemical action into rocks with new textures and or mineral makeups. And the analogy, and I'm hoping I'm not going to get blocked for showing you a YouTube video clip, but the analogy, if I have a YouTube video clip, the analogy is of a potter throwing a pot on a wheel. And that's what you see I'm going to let the music play a little, or the sound play a little bit. Actually, I'm going to turn it down. So you can just see what he's doing. And you know, this is what goes on with rocks too, but it's in the solid state. Wouldn't it be a pity if, as he's doing all this work throwing this pot, and then he puts it in a kiln to fire it, it melted into a blob of molten clay? I mean, all his work would be for nothing. Similarly, metamorphic rocks are changed from their parent rock to their daughter rock. That is the correct terminology. There are major changes that occur, but they occur in the solid state. Okay, so that means the rock doesn't become liquid and then recrystallize. If it did that, it would be an igneous rock. So, for instance, we have here a piece of limestone. And because of heat, it gets changed into a marble, and it would be not a good thing if that original limestone melted and then recrystallized. As I say, it would be an igneous rock, not a metamorphic rock. So that's what I mean by the solid state. And this pot analogy is a real good way to go with it. So we're going to stop there. I know you want to see the rest of it, but we need to move on to other things. Okay, so the deal is that, well, we'll let it play small there. The deal is that two rocks never fuse. So you never get these this piece of granite and this piece of basalt fusing together to form a metamorphic rock. That does not happen. If you subject them to that kind of temperature and pressure, they will melt and form an igneous rock. But you can take a parent rock like this granite and expose it to metamorphic conditions, and from it create multiple new metamorphic rocks. Okay, so having said that, what are the forces of nature that cause metamorphism of rocks. So he's finished with that wound. That's a nice pot. I'm always very impressed by people that know how to do that. So the forces that do metamorphism would include temperature and pressure. Those are the big two. But also there's a third one called chemical action we'll get to. We're going to start with temperature. As you might imagine, it takes a lot of heat to change a rock. Rocks can take a lot of heat before they got to get out of the kitchen, if you will. So where are some places that you would find that? I'm going to load up Google Earth here just quickly. I had it loaded, but I had to restart it because my screen recorder wasn't working right. So places that you find lots of increased temperature would be being close to a magma chamber. Okay, and so anywhere near a volcano, and of course Hawaii is a good example. There's a magma chamber underneath Hawaii, and rocks close to that magma would be exposed to metamorphic conditions. Also, if we back out a little bit here, if you go real deep in the crust, you're going to find increased temperatures. We've already made that point. So largely when we're talking about this, we're talking about something called the geothermal gradient. So let me back up for just a minute. How much temperature does a rock need to have before it will change? Well, you got to crank up the temperature 50 degrees Celsius over what we're currently feeling. So in our rooms, we're somewhere around 22, 24 degrees Celsius. Crank it up to about 70, 75 degrees Celsius. You're going to be pretty hot. You're not going to want to be there. You're going to begin to get a little change in the metamorphic rock. Crank it up to 200 degrees, a little more change, but that's low-grade conditions. The rocks can take a lot of that. They don't change a lot. You crank it up to just shy of melting. If you look at that under temperatures of 600 to 1200 degrees Celsius, it's considered high-grade metamorphism. That's, depending on the type of rock, it's just right there, just short of melting. So those would be low-grade and high-grade metamorphic conditions, anywhere from the low-grade 50 to 200 degrees Celsius up to just shy of melting. You're going to have rocks change due to heat. So that geothermal gradient, the idea that as we go deeper in the crust, so if you look at this diagram that I have here on the screen, depth increases as we go down, temperature increases as we go across. And so as you might expect, as we go deeper, the temperature increases. Okay, so we're about 100 kilometers deep right here, and the temperature has gone from 0 degrees to somewhere around 1300 degrees. Okay, so that's not a big surprise. Although, if you think about your kids in your future classrooms, what will their experience with going underground have been? Likely it'll be a cave. Well, when you go down in a cave, what's it like? Well, it's cold and damp and dark. Cold, though. So you're going to have to convince them that it actually gets hotter the farther down you go. Now, I've also put a link on Moodle to a 12-minute video. I want you to really I guess you'd have to really pay attention to minute 1 through minute 7:05. That's the key part, but it's only 12 minutes long, and I think it's kind of interesting. It's about the world's deepest gold mine and the conditions they experience as they go down deeper in the gold mine. And it makes this point that the deeper you go, the hotter it gets. And so you're going to need to come up with some way to convince kids that caves are an exception to the rule, that in fact the deeper you go, the hotter it gets. You might use the Alaska pipeline. That crude oil coming out of the ground on the north slope is really hot, and it cools as it goes south. So you know, that might be an example of something else that you could make the point with. So there are some places on Earth that you can go, though, where you go down a little ways. So you go down a little ways in the Earth, and the temperature increases a lot, like by those volcanoes or by Yellowstone. You don't have to dig down very far. This line would probably slope down much more sharply than it does in this graph. This is an averaged one. There are other places, like around here at Bethel, where you can go a long way down in the ground. The temperature doesn't increase much. So in that case, the line would be quite flat, something like that. And I should mention on this diagram here, this red line is the margin between solid and liquid rock, as it says right here. As you go deeper, it isn't just pressure that increases or temperature that increases, it's also pressure. And pressure is going to try to hold things in the solid state. And so there is, as I've talked about previously, a battle going on between temperature and pressure. And on this side of the line, temperature wins. On this side of the line, pressure wins. And so, yeah, around Bethel here, you could go a long way down. If you look in your notes, well, let me back up. A low gradient, no, I don't have to back up. That's where we want to go. A low gradient, like around Bethel here, would experience only a 10 degrees Celsius increase in temperature at the bottom of a 1 kilometer deep hole in the ground versus at the top of that 1 kilometer deep hole in the ground. Conversely, you go to a place like Yellowstone, and you're going to see a high gradient, where you dig a kilometer deep hole in the ground and the temperature at the bottom is going to be 40 degrees Celsius greater than at the top of the hole. In the case of Yellowstone, probably even a good bit more than that. Okay, so that's temperature. We go on to pressure. There are some places in the world where pressure is great. And if I back out of a consideration of Hawaii here just a little bit, and let's go back, let's go down to South America here. Here we have the Nazca Ocean Plate crashing into South America, subducting under it. How'd you like to be a rock right at the leading edge of where that plate is crashing into South America, making this trench? Boy, just think of the pressures that must be experienced by those rocks there. A great deal of pressure. So at plate margins where you have convergent or subducting plate boundaries. Another place where you'd see a great deal of pressure would be like, right here off the Gulf of Mexico, or off the Mississippi Delta in the Gulf of Mexico. So here's the Mississippi Delta. If you look down at the bottom here, way down here, you can see we're right at the delta. We're 0 feet above sea level, 1, 2, 3, 4, 5 feet below sea level. So pretty close to or just below sea level. Then if we go off the coast here a little farther, we drop down to 7,000, 8,000, 9,000 feet pretty quick. Well, a lot of this this stuff right here that makes up that slope is what's ever washed down the Mississippi River. That's sediment. And sediment gets progressively buried the deeper you go. And so the deeper it gets buried, the more time that transpires between the deposition of that sediment and whenever you want to look at it, that means there's going to be more pressure, more sediment on top of it, and more pressure. That's why this is also a popular place to go looking for oil. Organic material has been deposited along with the rock fragments in making this area of coastal Louisiana a good place to look for oil. Well, the deeper layers are going to have all the sediment on top of them, and they're going to be exposed to pressure. Of course, a rock can take a lot of pressure. And we're going to be looking at pressures in kilobars. 1 kilobar is 1,000 times the pressure you are currently experiencing. Right now, because of the weight of the atmosphere on top of you, you are experiencing 14 to 15 pounds per square inch. That would be like, believe it or not, about 3 gallons of milk sitting on 1 square inch of your body, pushing down on you. That's the weight of the atmosphere. It probably doesn't feel that heavy, but let's see, would it be that much? No, it wouldn't be that many. It'd be 2 gallons of milk. There's about 8 pounds per gallon, so yeah, somewhere in that ballpark. Gallon and a half, 2 gallons of milk on 1 square inch of your body. So we come to ignore that. Of course, if you go to the moon, there's not that atmosphere, so people bounce all around, like we'll show you when we get to astronomy. Well, rocks can take a lot of pressure. So 3,000 to 4,000 times the pressure that you're currently experiencing, that's what a rock can take before it begins to change. That's 3 to 4 kilobars. That's low grade. That means a little bit of metamorphic change. 12 to 15 kilobars, that's a lot of change. Above that, the temperature that comes with those increased pressures would probably cause that rock to melt. So as rocks experience pressure, they go through something. Here, I'm going to try another video again. Hopefully this doesn't get blocked. So this is an animation of what happens if you take a piece of granite, okay, just granite, and you expose it to metamorphic conditions. The minerals in it, So amphibole, that's hornblende. Okay, they're going to be changing in response to that. So be pressure from below, pressure from above, squeezing on that mineral. They're going to flatten those minerals out, and they're going to arrange them in layers called foliations. Okay, so if we go back to your notes, if you look at your notes then, that process of foliation is an important one. The pressure that some rocks experience, like Mississippi Delta, like at the leading edge of two convergent plates, that's going to cause three-dimensional minerals like quartzes and feldspars to flatten. Platy minerals, that's like talc, graphite, chlorite, flat minerals, biotite, muscovite, they'll move. And clay minerals, like that white kaolinite, they're going to reform into platy minerals. So you're going to end up with, bottom line, a lot of flat minerals. And that process then of arranging them in layers is called foliation. We talked about what you do with pumice. You exfoliate. That means you're taking off layers of skin, ladies, right? Well, a foliation is a layer. And so rocks have layers. And they're like ogres. So here's a piece of slate. It is itself a layer. Here's a piece of high-end, this is called migmatite. This is got lots of layers in it. And a little harder to see on this one. See if I can try, yeah. On the edge here, you might see some layers from the schist. So those layers are created by the pressure that the rock experienced. The last one is chemical action. So as hot water, I'm going to go to a different one here. Maybe I am. Yeah. So in this example here, we have a magma source that's going to heat the rocks around it. Water, if this is under the ocean, is going to descend through cracks and fissures in the overlying rock, get heated by that magma, and then rise up through it. And it's going to, as that hot water rises through the rock, it's going to change that rock. Oh, shucks. My computer wants to go on pause, so I'm just trying to keep that from happening. Okay, I know I could have paused the recording. That's okay. Here we go. Okay, so that chemical action will change things. It'll dissolve certain minerals away here as this hot water goes through the rock. And as it goes away from the heat source, it will cool. And as it cools to different temperatures, it will start depositing those minerals that it dissolved out of that rock that the hot water was going through. And it may even deposit them in certain areas. We're going to actually no, I'll show you that right now. So that's what can create what we call vein deposits. So in this case, this is a vein of gold, and it's actually in quartz that was probably formed as hot water heated by magma, moved away and through an overlying body of rock, dissolved the gold away, but then cooled. And as it cooled, when it got to this location, it cooled to the temperature where gold would come out of solution. There's another look. Here's silver doing the same thing. Here's a vein of silver. And then lastly, here's a vein of copper. Okay, so that's going to occur because of the movement of that hot water, that chemical action. So metamorphic rocks then, given all three of these forces, the two major, temperature and pressure, the more minor, chemical action, they are going to result in low, medium, and high grade metamorphism, depending on how much of each of those forces the rock is exposed to. And so the idea is, if you take this piece of granite and you expose it to a little temperature and pressure, it's going to change. A lot of things are going to happen to it, but one of the things is you can get this piece of slate. Now, this piece of slate, I shouldn't have held up granite. It's more likely to come out of a piece of a sedimentary rock, which we haven't had yet. So here you got a piece of sedimentary rock called shale, okay? And the shale will be changed with a little heat and pressure into a slate. Now the thing with the slate is, it's just a dull gray rock. It's what you walk on when you walk in the CLC. See if I can do this here. Yeah, you can kind of, I'm hoping you can pick up the sound difference. If I drop the shale, it's got a clunky sound like that. But notice when I drop the slate, it's got a higher pitch sound. There again. I'll do this again in lab, but there's obviously been a change as that original shale rock was compressed and changed, metamorphosed a little into a slate. Well, if you crank up the temperature and pressure a little bit more, a rock like this slate can be reformed into a rock like this phyllite. Now, I'm hoping you can see the shiny nature of phyllite. It has mineral crystals that are just a little larger than with slate. And so they will have cleavage planes that reflect back at you. You can't see them, though. They're still very small. They're bigger than slate, but they're not big enough to see the individual cleavage planes of these mineral crystals yet. But you still get a satiny sheen over the whole surface of the rock. Crank up the temperature and pressure a little bit more, and you get schist. And that's what we got here. This one had the predominant mineral is mica, but here you can definitely see facets of different cleavage planes as I move it around. Crank up the temperature and pressure a little bit more, you get gneiss. Okay, gneiss, you can see alternating layers of light and dark minerals as they migrate to different areas in the rock. The most extreme case is this one here, this migmatite. Now, if you remember, well, I guess maybe you don't, so I don't know if I talked about it. So the lighter colored minerals are the ones that will melt first. And so in this rock, there are light colored bands and dark colored bands. More dark than light. That's because the light actually melted. This almost went igneous. But most of the rock is that dark gray and had not melted yet. And so we would say that because most of the rock stayed that dark gray color, didn't melt, that we would call this still a metamorphic rock. And it's called migmatite. It exists right at the boundary between metamorphic conditions and igneous conditions. All right, last thing. So generally on Earth, you find three places where metamorphism occurs. Metamorphic rocks are probably the least common type of rock. We find a lot of them around here because we're in a shield region of our continent, but generally speaking, they're not as common. So contact metamorphism, that's the kind of change in rock that occurs when it's close to a magma source. So if this is surrounding rock, and here's the magma intruding into it, this margin right here between the magma and the surrounding rock will be changed because of the incredible heat it is exposed to. Oftentimes there's not much pressure to go along with that, just a lot of heat. Okay, that's contact metamorphism. Contact with a magma source. Regional metamorphism would be like I described before, when you have large areas of tectonic plates, well, here's deep burial of sediment, like off the Gulf Coast of the Mississippi Delta, or we can just go down here, the Caribbean plate, as it's moving east and slamming into the Pacific plate. So that contact zone along that whole region would be a place where metamorphism occurs, and you have regional metamorphism. Lastly, hydrothermal metamorphism, that movement of hot water we talked about with chemical action. That hot water can come from, if you remember, volatiles in magma. Could be water, so you can get juvenile water there. Metamorphic water, yeah, you can squeeze a rock so hard that you can get water out of it. And then groundwater, ocean water, can seep down in and be a source of water that can cause metamorphism. And we already talked about how that hot water can cause vein deposits. Okay, so that's about what I had to say about metamorphic rocks, and we'll get a chance to look at them in lab on Tuesday of next week. You have a good day. As I said, I will have a video on here describing the brief activity that I want you to come into lab at some point before next Tuesday. The sooner the better, and I want you to set this up. And we already made rock candy to see how crystallization occurs out of a melt, like magma. Now we're going to do mineral formation, rock formation lab, looking at minerals and rocks that would form as water evaporates and deposits those minerals. And again, another good activity you can do with your class. I will have a handout on Moodle, as well as a stack of them in the classroom for you to look at. It's a single page, and it's a good activity that you can do in your own classroom, and I think you'll enjoy it. Thank you.